So let us now solve problem number 9. We are given that we have a particle on which we apply a constant force F, and due to this constant force F, it moves from its position of rest to a motion, and it experiences a resistive force minus BV, and we have to calculate the speed of the particle at any instant of time t. So for a particle on which a constant force F is applied, and if it is moving in the rightward direction, then the resistive force will apply in the other direction, in the opposite direction of the applied force, that is opposite to the direction of the motion. So I can write F minus BV is equal to m dV by dt. This is our equation of motion. So if I now write this equation like this and divide it by mass on the both side, this cancels out and I will get F by m is equal to dV by dt plus B by m V. So this is our differential equation that we have to solve. So this is our first order differential equation, and to solve this equation we have to use the concept of integrating factor. So F by m is equal to dV by dt plus BV upon m. This is our first order differential equation, and to solve it we have to first evaluate the integrating factor, which is e to the power integration b by m dt, which changes to e to the power b by m t. So multiplying the equation by this factor on the both side, I will get I f by m e by b by m into t is equal to dv by dt into e to the power b by m t plus b by m v into e to the power b by m t. So I can use the product rule for differentiation here and can write it as d by dt of v into e to the power b by m t, which is equal to f by m e to the power b by m t. Now I will take dt to the left side and will get f by m e to the power b by m into t dt is equal to dv e to the power b by m t. Now integrating on both sides, I will get v into e to the power b by m t is equal to integration of f by m e to the power b by m t dt plus a constant of integration c1. So v into e to the power b by m t is equal to f by m into e to the power b by m t upon b by m plus c1. So m in cancel out and v is equal to f by b plus c1 e to the power minus b by m t. I have divided by e to the power b by m t on the both side and finally got this expression. And now we have to find c1. So now we will use initial condition that at t equal to 0, v is equal to 0. So if v is equal to 0 at t equal to 0, then f by b plus c1 into 1. So c1 is now equal to minus f by b. So v as a function of time will now be 1 minus e to the power minus b by m t. So our answer is C, and this is our correct answer. So we see how we can use Newton laws of motion to write equation of motion and use differential equation to find out the velocity time dependence of the velocity. So let us say the body is moving in the upward direction, and this is equal to v equal to v naught, that the initial velocity is v naught, and at the highest point v is equal to 0. So at any instant of time, I see that the forces acting on the particle is Vg, and that is the weight of the body, Wg, and the drag force in the opposite direction of the motion. So if the particle is moving upward, then the forces acting are Wg, that is the weight in the downward direction, and the drag force in the opposite direction of the motion. So my equation will be m dv by dt is equal to minus mg minus bv square. So we are given that the particle is of unit mass. So let us now substitute 1 for the mass. So this will go out and this will also go out. So we are just left with this equation. So we have to basically know the we have to formulate a relationship between velocity and height. So let us say I multiply by dx and divide by dx on the left hand side. So this will be equal to minus g minus bv square. So my differential equation will change to v dv upon dx. So if I take the term on this side, this will be g plus bv square, and this will be equal to minus um, dx. So if I want to integrate this expression to the left, I have to take g plus bv square equal to some constant beta or a new variable beta. It's just integration by substitution. So this will be g plus bv square, which is equal to beta, and if I just integrate it with respect to v and beta on both sides, differentiated by beta and v on the both sides, I will get b 2 v dv is equal to d beta. So dv in v dv is equal to d beta upon 2b. Then I will substitute the value of v dv over here. So I will get ln beta. I will substitute the value of beta over here. Ln g plus beta v square is equal to minus 2bx plus an integration constant k. So if I change this, the expression will change to g plus bv square is equal to k into exponential minus 2bx. So this is the equation for the upward motion. So if I take the initial condition that at x equal to 0, the velocity of the particle is v naught. So g plus beta v naught square is equal to kappa into 1. So my expression will change to g plus bv square is equal to g plus b v naught square exponential minus tbx. So this is the value of k. I got it by x equal to 0. The velocity of the particle is v naught. So this is the expression, and I can use another initial condition that at x is equal to maximum height, say let's say h, the velocity of the particle is 0. So when the particle reaches its maximum height, let's say h, then the velocity of the particle will be 0. Then my expression will be g is equal to mm, g plus bv naught square exponential minus 2b h. If this height is equal to h. Okay, so this is our x2 thing that we have got by using this is the thing that we have got by using the initial condition. We first calculated the value of the integrating constant k by using the initial condition that at x equal to 0, v is equal to v naught, that is the initial velocity, and at the highest point, let's say at h, the velocity is equal to 0. So now let us do the same calculation for the downward motion when the particle after reaching the maximum height falls down. So my equation will be m dv by dt is equal to mg minus bv square. So this is the equation that I will get if the particle is moving in the downward direction, because mg will be higher than the drag force. That's why the particle is moving downward. So if I now substitute the value of unit mass on both sides, my equation will change to this. And now by using the same integration technique, I will get dv by dx, v dv by dx is equal to g minus bv square. So v dv upon g minus bv square is equal to dx. So let us integrate on both sides, and to integrate this expression to the left I will use the same technique that g minus bv square is equal to num constant, say beta dash, and beta dash d beta dash is equal to minus 2b v dv. So after taking derivative on both sides, I will get minus 2b v dv is equal to d beta dash. So the integration will be ln g minus beta v square is equal to minus 2b x plus ln c1. So this is our new constant of integration. So to get the value of c1, I will use the initial condition that at x equal to height h, that is at x equal to 0, that is at the maximum height, that from x equal to 0 to x equal to h. So at x equal to 0 velocity is 0, so ln g is equal to ln minus 2b 0, which is equal to a plus ln c1. So ln c1 is equal to ln g. So ln c1 is equal to ln g. Now substitute the value of ln c1 over here. I will get ln g minus bv square upon g is equal to minus 2bx. So changing it into the exponential form, g minus bv square is equal to g into exponential minus 2bx. So let us now again use the initial condition that when the particle reach the downward to the ground again after reaching the highest point, it covers a distance x is equal to h. So g minus bv square is equal to g exponential minus 2b h. So when it reaches the fall to the same height h, this will be our at x equal to h, v is equal to, we have to calculate. So when it reaches reaches down in height h, we have to calculate v. So we have used this condition, this initial condition, that after reaching the maximum height, that is, the motion starts again, and from it will start to move from x is equal to 0 to x equal to h. So by using x is equal to 0, where v is equal to 0, I have calculated the value of ln c1, which is equal to ln g. So by using another initial condition, that x is equal to h, that is at the point when it just hit the ground, when it returned back to its original position at x equal to h, I have to calculate the v. So by using the value of exponential minus 2bh from the previous upward motion, I can substitute this exponential minus 2bh. I will get g minus bv square is equal to g into the value of exponential minus 2bh is g upon g plus bv naught square. So by multiplying on the both side, taking this term to the other side and cross multiplying, g square plus gbv naught square minus gbv square minus b square v naught square is equal to g square. G square cancel out on the both side, and after taking b common, I will get g v naught square minus g v square minus b v square v naught square equal to 0. So g v naught square is equal to g v square plus b v square v naught square. Okay, so after taking v square common, I will get g plus b v naught square and g v naught square. So taking g common from the right hand side, I will get v naught square is equal to v square 1 plus bv naught square upon g. Okay, so I can take this expression to this side and can take the under root. I will get v naught upon under root 1 plus bv naught square by g is equal to v when it reaches the height h. So when the particle, after moving upward to the downward at point x equal to h, the velocity of the particle will be this. So we just saw how we can separate the upward motion and the downward motion, and can formulate two differential equation, and by setting up a relationship between the two different motion, I can find the velocity of v. So this completes this question. So let us now study or solve another question. So let us now solve question number 11. We are given that we have a object of mass m that is thrown vertically upward, and it is acted upon by a constant resistive force F, and if t1 and t2 be the time of ascent and descent. Ascent means if the particle is going from its initial position to the final position, that is at maximum height, it is the time of ascent. If it is going upward to a maximum height, then it is the time of ascent, and if it is moving downward from the point of its maximum height to the ground, it is the time of descent. So we have to calculate the ratio of the time of ascent and the time of descent. So in general, we know that S is equal to ut plus half at square. So if the distance is constant, so we see that the relationship between acceleration and time is 1 by t square. So a the acceleration is related to 1 by t square. So using this concept, we will try to solve this question. So let's say if the particle is moving upward, that is if it is moving upward, so so particle or the ball is moving upward and it reaches a maximum height, let's say h, then the force body diagram for the particle is mg downward, and if it is moving upward then the resistive force is in the downward direction f. So m into a is equal to minus f plus mg. This is minus, so a acceleration is equal to f by m plus g if the particle is moving upward. If it is moving upward, so if the particle is moving upward, then the acceleration for ascent is this: a is equal to f by m plus g. Now let us say if the particle is moving downward, and if the particle is moving downward, so the gravitation, if I draw the force body diagram, then gravitation mg is acting downward and the resistive force is in the upward direction, because if the particle is moving downward, then the resistive force will act in the opposite direction of the motion. So now the acceleration ma is equal to mg minus f. So if I write acceleration in the downward direction ad is equal to g minus f by m. So if the particle is moving upward, then this is the acceleration of the body for the motion of ascent. That is, if it is moving upward, it is ascending. That is, it is going to a maximum height. Then this is the upward acceleration, and this is the downward acceleration when it is descending. That is when it goes to the ground from its maximum position. So as we saw that the relationship between acceleration and time is this. So a upward is proportional to 1 by f by m. A upward is equal to f by m plus g, which is proportional to the, sorry. So let us now see how to evaluate the relationship between time. So a upward is equal to f by m plus g, which is proportional to 1 by t1 square or t upward. Okay, so and acceleration downward is equal to f by g minus f by m, which is proportional to 1 by t2 square downward. So if I now divide these quantity 1 and 2, I'll get, by dividing quantity 1 and 2, I'll get the correct ratio for the time, the rate ratio between the time of ascent and time of descent. So f by m plus g upon f by g minus f by m is equal to 1 by t1 square, that is upward, divided by 1 by t2 downward square. Now if I change the sign for the division to multiplication, then the t2 will go upward. So this is our ratio: t2 by t1 is equal to f by m plus g upon g minus f by m, 1 by 2. And we are asked what is t1 by t2. So t1 by t2 is equal to g minus f by m upon g plus f by m under root. So this is our answer. And from the option we can see that option D matches our answer. So this is the correct value for the ratio between time of ascent and time of descent. So let us now try to solve this question number 12. The question says we have a particle that is thrown with an initial velocity v0, and during the motion it experiences a drag force of minus kV. That is, the drag force depends on the velocity of the particle, and we have to calculate the distance with respect to time, that is x of t, x which is a function of t. So for a motion of a particle in a medium where it experiences a drag force or a resistive force, if the motion is happening in this direction, then the resistive force apply in the opposite direction. So for this type of motion, I can write F is equal to minus kV. So using the definition of force, that is m into dv by dt, I can write m dv by dt is equal to minus kV. So I can solve this differential equation by you taking v on the left side and minus k by m into dt. Now integrating both sides, I get ln v is equal to minus k by m t plus ln c. So if I substitute the value, or if I use the initial condition that at t equal to 0, v is equal to v naught. So ln v naught is equal to 0 plus ln c. So value of ln c is ln v naught. So by substituting the value of ln c in this equation, I will get ln v by v naught is equal to minus k by m t. So v is equal to v naught exponential minus k by m t. So if I just plot the graph of velocity versus time, I'll see that the velocity will decrease with time because of this exponential function. So we see that in case of a motion in a medium where the particle experiences a drag force, the velocity decreases with time. So let us now evaluate what is the dependence of distance with respect to time. So let us calculate x, which is a function of t. So we had v is equal to v naught exponential minus k by m t. So using the definition of velocity, which is dx by dt, which is equal to v naught exponential minus k by m t. So dx is equal to v naught exponential minus k by m t dt. Now integrating on both sides, x is equal to v naught exponential minus k by m t upon minus k by m plus a constant of integration c1. So if I now use in initial condition again that at t equal to 0, x is equal to 0, that is particle is just at the origin. So 0 is equal to v naught minus k by m plus c1. So c1 is equal to v naught m by k. So substituting the value of this constant of integration over here, I will get c is equal to v naught m minus on k exponential minus km by t plus mv naught by k. So if I now take common mv naught by k common, I'll get 1 minus exponential minus km by t. And if I just plot the graph of x versus t, the kind of graph that I will get will be like this. So the position is increasing with time, but at every instant if I draw the slope of the graph, I will see that At some instant, it will become parallel to the t-axis, that is, the slope will turn out to be equal to 0. And if the slope at this point turn out to be 0, then means dx by dt equal to 0 means that velocity is equal to 0. So when the particle is in a viscous medium, it will lose its velocity with time, and this is the expression for position in terms of time for a particle in a motion in a viscous medium. So let us now solve more problems.